So we continue our discussion. So previous lecture, we already talked about the co-ed flow. So we have three conditions. So and now we are going to discuss about the Pouseuille flow. So the major difference between co-ed and Pouseuille flow is actually reflect the flow inside a pipe. So when the flow inside the pipe, so it is quite similar with the idea of this third condition of co-ed flow. So because the third condition of co-ed flow, so if you have two plates with lubricant or not lubricant, the liquid between two plates. So but the difference is in co-ed flow they assume that the flow is in natural flow. So that's why in the diagram, they will show that the flow is downward. Okay, but in co-ed flow, in Pouseuille flow that we are going to see right now. So it is more about the flow in pipe.
Excuse
So
me, Doctor.
yes,
Just now the notes number one you haven't finished, right?
yes, that's it, the calculation of co-ed flow using the idea of Navier-Stokes. So I discussed it. I just show you the about that on the first at the middle of the lecture. That's actually the same idea.
Okay, okay.
Okay. So I bring that one with a simpler idea of means you start with the Navier-Stokes equation and then you simplify everything. Okay. So I think if you read that notes first, if you don't understand, you just WhatsApp me.
Okay, Doctor.
Okay. So this is actually the same idea. Okay. 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 So the difference is that's why in Poisson flow. So we are discussing about the flow which is upward like this one because it is not natural flow. So it is for fluid. It is not possible to flow in natural way from the lower surface to the higher from the lower elevation to the higher elevation like this one. Okay, and for the Poisson flow, so we prefer to use a circular cross-sectional pipe. Okay. So why? Because in circular cross-sectional pipe, we need to change the terms instead of Cartesian coordinate into the polar coordinate. So we cannot use the x and y anymore because we need to relate with the radius of that pipe. Okay, so this is the, for example, we have a cross-sectional pipe like this one. So we have the circular cross-sectional area. So, and then again, it starts with the same idea. We have a small element of this one. So, and then with this small element, so we assume that a few forces act on that element. So first is pressure, force according to the pressure. Okay, it will act like this. Okay, because force need to push on certain surface. So because we assume that our element is like this cylinder shape, so we assume that the force will act like this one. So, and then we have forces according to the shear stress. So we have this one. So and then we have a gravitational force. So we have uh, the gravity pull on this axis, and because we are calculating the force, so we take this axis is our main concern. So we need to take the distribution, the component of this weight of this gravitational force, and it will become W times sine alpha. So which is the sine alpha is the inclination angle. Okay, so I think you could understand this one. Okay, so and then the second one is you need to understand that to calculate the shear stress here, okay, to calculate the shear stress here, so we okay, so this is the shear stress. So we have force is equal tau and A. So and then we need, I hope you could understand to determine the correct cross section, the correct area, because this area is actually reflect the area where the shear stress act. So for example, we have an element of cylinder like this one. So mean that on the surface there is a lot of molecule that have shear stress. So means that the A here is the area of this surface. Okay. So please do not make a mistake. The A here is not the cross-sectional area for the cylinder. So it is the surface of shear stress. So that's why here in the equation will become 2 pi r and delta s, because 2 pi r means if we have a cylinder like this, so 2 pi r means the circumference or the perimeter of this one, and delta S is the length of this element. So mean that 2 pi r and delta S will give us the total area where the surface area, act. Okay, where the shear stress act. Okay. So here the arrow is actually it's reverse to the fluid direction, and then please imagine that this is about the circular shape like this one. That's why the arrow is actually on the one side. So it is totally different. The situation is different when we discuss about the co-ed flow. So in the co-ed flow, so we have a plate here and also plate here. That's why we have shear stress in both direction like this one, because the nearer the fluid the molecule to the solid surface, so mean the shear stress will increase. Okay, that's the different. So and this arrow is actually is represent all the direction at the circular element here. So means that the shear stress here will act like that one and so on. So that's why it is enough for us just to show one arrow here. Okay, so please understand that this arrow is actually to reflect the shear stress that acts on the circumference of that element. Okay, so another thing I think you could understand. So okay, next one. Okay, we start to use the radius of the pipe. So and then we need to change between the idea of R and also the idea of Y. So later on I will explain in this calculation. So we start with the same step, so which is the Fs here. So means the total force is equal to 0 in equilibrium. So we calculate all the value here. So we add the pressure force, the pressure times area. So we have the weight, okay, the component of weight, and also the shear force like this one. And then we could calculate the weight here. So weight is equal to mg. So this is the rho g. And then the m here can be calculated by using the idea of rho g and okay m. Okay, I'm sorry. So m is equal to rho and volume. So and g will remain as g here. So and the volume here is actually the A times S. So we have the A times S here is volume, and gamma here is actually consists of rho and g. So I think you could understand all of this. and sine alpha is all equal to dz over ds, and now we use the positive sign because the flow is actually from the bottom to the top, so it is upward, like the figure shows. So after you sum all the all the forces, so you will find it will become like this one, and then we divide equation 2 with delta S and A, and then we could simplify the shear stress is equal to this one. Okay, so here, okay, according to the gradient, so we found that the dPds is negative and constant across the section of uniform flow. So because the dP rho z, it follows that dP rho z will be positive and constant across the pipe section. So it means that it is negative across the section of the uniform flow. It will be positive and constant across the pipe section. So the pipe section, dP, okay. So I think, okay, so we start with this one. So first, so we determine how the velocity varies across the pipe in substituting tau in equation 3. It's equivalent to mu dv dy, and we need to integrate this one. Okay, so the main idea of this one is, okay, we know that tau is equal mu dv dy or tau du dy. Okay, so we have tau equal mu dv dy here. But the problem is we need to change from the Cartesian coordinate into the polar coordinates. So we use the idea of dv dy is now equal to negative dv dr. So this relationship depends on our observation. So the observation is, okay, so if we see this image, okay, so this is the radius. So, and normally in co-ed flow, so we will take the value of y will equal to 0 at this bottom, and then the value of y will increase along this direction. So it means that if we, according to idea of y, so if y equal to 0, so means that the value, because we have no slip condition here, so the velocity is equal to 0. So however, for if we interpret the velocity according to the polar coordinates, so we will find that the value of r equal to 0, mean r equal to 0 is actually at the center of this pipe. So the value is equal to maximum. U will become U maximum. So so R maximum, so mean when R here as at this surface, then the U will become 0. And for Y here is when Y at the center of the pipe, so mean Y is equal to R, so the velocity will become U maximum. So if you see this one, so if you draw a graph, so you will find that the graph is actually, the gradient of that graph is actually reverse. So that's why we make assumption of dv dy is actually to minus dv dr. Okay, please assume like this, because this is the explanation of Pouseuille. So because Pouseuille changed the orientation from the Cartesian coordinate to the polar coordinates. Because in any textbooks, they will not write tau mu du dy in terms of polar coordinates. There is no idea of shear stress written in polar coordinate. Normally, we will assume that tau is equal to mu du dy. So you need to understand that tau is equal mu du dy. Okay, so actually u here is the linear velocity. Linear velocity means the unit is in meter per second. Okay, so and then we change that one. So we bring the mu to the right. So and then we change dv dy into negative dv dr. So we bring the negative sign to the right hand side. So and then we integrate, and finally we could get this term plus C. Okay. So and then again we could give the R equal to R0, mean the maximum R will give us velocity equal to 0. Then we could get the value of C here, the constant of previous equation here. So and then if we substitute, so the equation of 6 will become full terms like this one. Okay, so again here the ds here is actually only act for z. So if you expand this term, so it will become negative ds for negative ds for rho and g, because this rho and g is actually can be simplified as gamma. Yeah, so gamma is also called as a specific weight. Good, because American like to use gamma. So if you read a textbook from Americans, so you will have they usually change everything into gamma. So but British I think is good. Yeah, it's like to maintain in rho and g. Okay, I personally like to maintain rho and g because it is 2 parameter. So I like to see that both parameter instead of a gamma. Okay. Okay, so means that that equation, so this is the equation that we have. So it's actually proposed by a Frenchman called Pouseuille, okay, who studied this low speed tubes in 1840s. Okay, so this is the Pouseuille flow. So it is more about the flow in pipes, and usually it shows that the flow is actually upwards like this one. Okay, another thing that you should understand that the shear stress is actually reverse. It shows the reverse trend with the velocity as shown in this diagram. So you will find that at r equal to maximum value, r naught, so the velocity is 0 because it is no slip condition, and then the velocity will become maximum at the center line, so at the center point, at the middle of the pipe. So and at this line, so you will find that the shear stress is at minimum, so we assume that it is equal to 0 because so it is the distance from the pipe wall is the longest one. So and then but the at r equal to r naught, mean r at the maximum value, so the shear stress is become maximum. So this is what this diagram try to tell you. So this is the equation that normally used for the Pouseuille flow. So means that if you could remember this equation, any problems regarding to flow in pipe can be used. Maybe you could start with this velocity distribution. So this is the discussion against same like the co-ed flow. So we try to calculate the flow rate. So I think you already know why we integrate V times dA. So dA here, so it might be different from the co-ed flow, because in co-ed flow we just use dy because our element, our control volume there is in rectangular shape. So but in Pouseuille flow we assume that our element is in circular, in cylinder shape. So we use dA here, and dA here is actually 2 pi r dr. Okay, I hope you could understand 2 pi r dr because we have a cylinder like this one. Okay, so if this is the center point, okay, so the area that have same velocity is actually in ring condition like this one. So mean at this area, so the velocity will show the same amount, because you must know that this area has same radius. Okay, so the dA here is reflect the area of this ring area. So the area of this ring is actually 2 pi r dr. Okay, I already explained about this in previous class. Okay, so and then so if you calculate this one, so you will get the Q is equal to this one, and then we give the limits of 0 to R naught. So finally we could get this term. Okay, so and then again from this flow rate, we could calculate the average velocity. Okay, so we divide, you know, V is equal to Q divided by A. So and then you could divide by 2 pi R. Okay, okay. You will divide as pi r square, because this area is actually the total area of the pipe, not the area of this ring element, because we already get the total flow rate for this pipe. So means that we will divide with the total cross-section area here. So it's the area of the circle is pi r square. So we divide by pi r square. So we have r square here. So I think you could see the changes of the terms. So this is the average velocity. So and then we could have this one, and then we could found that the average velocity is actually the velocity maximum divided by 2 only. Okay, so it is different between the co-ed flow. So the co-ed flow is actually 2/3 from the U maximum. Okay, that's the assumption that we could get from this calculation. So next, another one, this is actually to a discussion if we substitute the value of R is equal diameter divided by 2. So we could get this term. Okay, but why? Because we want to prove about the actually the equation for losses in pipe, as I said previously about the major loss, minor loss, and so on and so forth. So we use the term of in term of diameter. So and then we substitute the R is equal to D/2. So and then we have this one. So and then we have that the differential of pressure and Z here, okay, will give us minus 32 mu velocity over D square. So and then what is this mean? So this is actually the losses. Okay, because if we this is actually from the Bernoulli equation. Okay, so we have the pressure difference. So and then we have the potential difference. So this is rho g and z. As we know that rho here is rho g. So and then we have the z here. So this is actually from the Bernoulli equation, because normally people will use that P over rho g plus V square over 2g and plus z. So some textbook, they will use the terms of rho g here. So mean you multiply all this term with rho g. So you will have P plus V, and then the Z here will become rho G Z. So that is what we have here. And this term is actually will become the velocity head, the velocity different here.
Doctor, excuse
Yes.
me.
Yes.
For Z1 and Z2, these are the elevation from the zero axis?
Yes. So the Z1, Z2 is like a Bernoulli equation. For example, if you have a pipe like this one, so this is 0.1 and this is 0.2. So Z2 minus Z1 mean the height of Z2 here is minus the Z1 here.
The distance between Z1 and Z2.
Yes.
Okay.
Okay.
Thank you.
Okay. Okay, so this is actually, as I said, just to show from the Navier-Stokes equation, means from the Pouseuille flow, we simplified, we get the terms here, and then finally this term is actually could reflect as a HF, mean the losses in pipe. Because I think previously you already know how to calculate the major loss, minor loss inside a pipe by using the Bernoulli equation. So one of that equation is actually the losses is actually come from the idea of Pouseuille flow. So means that you start to it start from a small particle, a small element that you take from the flow in pipe, and then you calculate all the forces that interact with that element, and then finally you get the total flow rate. You calculate the average velocity, and then you could find that it will give you an extra term. So an extra term here. So if you, okay, it start from here. So mean if you calculate everything, you rearrange the equation, so you will have this term, and then finally if you rearrange it back into the normal Bernoulli equation, so we have P, we have Z here, so and then you will find that this is an extra term that we get from our Bernoulli equation. So and then here in our Bernoulli equation here, so there are no velocity. Why? Because we assume that our diameter of our pipe is constant. So you know that if the Q is constant, the flow rate is constant. So and then if the cross-sectional area is constant, so mean the velocity is also constant. So if we have the velocity at 0.1 here and also the velocity at 0.2 here, so we could easily cancel off the value. So that's why in this term, the value of velocity is actually already cancelled. So and then the extra term here is actually the losses. Losses means the resistance that fluid need to overcome before it could reach to its desired destination. So I think you already know about the losses of inside a pipe flow of this one.
The surface fraction, you mean?
Okay, the losses is divided into two. One is major losses, and another one is the minor losses. So the major losses is actually the friction, the losses or the consumption of energy to overcome the friction of the shear stress, at the surface of the inner surface of the fluid, or at the inner surface of the pipe.
Yes.
Okay. So the minor losses is actually the energy consumption when fluid go through a component parts of pipe. For example, you change your diameter from the bigger pipe to the smaller pipe, or you put a valve, for example, or you just bending, you put a 90-degree bending. So now the energy, the fluid flow need to slow down the velocity and to take a corner. So and then it will flow into the its own back to its normal velocity. So that's called a minor losses.
Excuse me, doctor. For these two types of losses, major and minor, for both of them, we will use this equation: 32 mu L V over sigma D square.
Okay. So the basic idea is, okay, I will explain here. Okay. So this is the simple application that uses losses. So for example, we have a tank here. Okay, so let's say we have a source of water here. So and then we bring this into a very long pipe. Okay. So as you know that if the inside velocity here is 10 meter per second, okay, so the velocity that comes out here is actually not 10 meter per second, because the flow is weakening, because it needs, okay, the velocity is weakened, is reduced.
Yes.
Okay, because the flow, the energy from the fluid needs to overcome the resistance caused by the shear stress. Okay, so for this one, okay, please take this as point number 1, and please take this as point number 2, for example. Okay, Okay, so and then we develop the velocity. We develop the Bernoulli equation. So at point number 1 here, so we have P1 over rho G plus V1 square over 2G and plus Z1. So at point number 2 here, so we have P2 over rho G plus V2 square over 2G and plus Z2 and plus HF. Okay. So that's why the velocity that comes out at this one will become decreased because a part of that energy, a part of the pressure, velocity, and the potential energy need to overcome the friction along the pipe. That's why if you see the equation here, it has the value of L here, the L and the B, because it reflects the bigger the surface that contact with the fluid, so means the higher the friction. Okay. Okay, so that is the usage. Okay, might be you are confused. Okay, in this term, you will find that there are no velocity. So this term is actually derived from our diagram here. No, this one. Okay, from our diagram here. That's why we assume that we have a same cross-sectional area here. Then the velocity can be neglected because the flow rate is constant. Okay, I hope you could understand that.
Yes,
okay.
yes.
Okay.
Thank you.
So this equation is actually based on the real Bernoulli equation because from this calculation, we'll already get the value of HF. Okay, so we have here HF is the frictional resistance. Okay.